Good morning. Welcome to the course on smart materials and intelligent system design. Now, we are coming to the module 3 of this course. So, in module 1, I have given you the overview of the smart materials, and in module 2, I have talked about the composite materials. Also, module 3, I have told you about the mechanics of composite materials. So, this is module 3, in which we are going to now, aided by all the backgrounds that we require, we are having now the how to model. We have reached the stage that how to model the piezoelectric materials. Okay. So, this is I think that all our background knowledges, particularly the mechanics of composite materials and the overview of smart materials, will help us to rebuild the equations, the governing equations now. So, when we will talk about modeling of such smart materials, like we will start with the piezoelectric materials, we have to keep in our mind that a piezoelectric material has both an electrical model, in which you can consider it to be a voltage source along with a capacitance attached to it, and also you can also consider the mechanical model of it. So, in the mechanical model, it is some kind of a spring system. Okay. So, you have a mechanical model and you have a electrical model of the system. The point is that when we will consider the piezoelectric material as an actuator, these two has to get integrated with each other. So, we have to look into it how it gets integrated with each other, but with the use of constitutive equations, and that is what we will be looking at this stage. So, I will first talk about remind you about the fundamental equations of piezoelectricity that we had initially discussed. We will re-emphasize on the piezoelectric coefficients. Some of the coefficients are very important for us. Then different piezoelectric materials and their properties, and we will get simplified equations for a piezoelectric patch, active strain expressions, how to get the active strains, and one typical Euler-Bernoulli model of the problem as actuator. So, this is what we intend to do in this short lecture. The fundamental equations of piezoelectricity, this time I have represented it in terms of tensorial notations. Okay. So, accordingly, this is the stress tensor, which is known to you as sigma I j, and S is the strain tensor, which is also known to you. The electric field, as you can see here, that the electric field intensity that is coming up here, and d k I j is actually that piezoelectric constants that is there, that is relating this electric field intensity with the stress tensor, and you have the electric displacement field, and once again you have we are relating it here with the strain tensor and the electric field intensity. So, this is the overall tensorial notations of the system, and with this system we will now see that how we can develop the governing equations. Now, there are 4 constants, piezoelectric coefficients, so to say, which are actually important for us. Okay. Piezoelectric charge constant, piezoelectric voltage constant, electromechanical coupling factor, and frequency constant. So, when we will be discussing about it, keep in mind once again that the planar part is represented by x 1 and y 2. So, that is the planar part, and the transverse direction we are representing it by z or 3, that is also the Pauling direction. So, with this axis system in mind, let us look into the piezoelectric coefficients. So, the first important one is the piezoelectric charge constant, that is constant d, and in this case this is d 31. So, what it means is that I am either applying voltage along the 3 direction and getting the deformation along one direction, or I am applying stresses along one direction and getting the voltage along the perpendicular direction. D31 and D32 are generally considered to be same, but they may differ because there can be some anisotropic materials where it will be different, and D33 of course, in which you are doing everything along the 3 directions, that means along these directions. Okay. So, you are applying stress along the 3 direction, you are getting voltage from the 3 direction, or you are applying voltage along 3 direction and you are getting deformation along the 3 direction, which is used in the piezoelectric stacks. So, D31 as you can see will be finally an unit of charge over force, or you can also have the unit in terms of meter per volt. So, basically for all these piezoelectric charge constants, the units could be either in terms of meter per volt, which is following this part of the relationship, or it can be in terms of the sensor part of the relationship, where it is picocoulomb per Newton. So, the relationship this constant itself is telling us that in one case force is generating the charge, that is the picocoulomb per Newton part, okay. That is where we use it as a sensor, and in another case the voltage is developing the deflection in the system. So, the unit itself is amply clearing it. The other point is that instead of coulomb per Newton, we are using picocoulomb because the capacitance is generally quite low. So, this is a very important constant, piezoelectric charge constant, that we will be using. What is the other constant? Well, the other one is G, which is piezoelectric voltage constant. In fact, this is used more in terms of sensors. So, in this case the ratio that we take is voltage over force per unit width of the system, or force per unit thickness of the system for G32, or G33 is voltage over time and the force per unit area of the system. So, this is used mostly for the sensorial equations, and in this case the unit is voltage meter per Newton. Then another important constant, I also told about it to you earlier, it actually depicts the actual energy transfer from electrical to mechanical energy or vice versa. So, in this case it is the ratio of electrical energy to mechanical energy, which is given by k square, okay, and k is called the electromechanical coupling coefficient. If k is very close to 1, which means the complete energy is getting transferred. If k is much less than 1, it means it is not, the material is not very much piezoelectric. So, k actually tells us what is the degree of piezoelectricity that is there in the material. Now, one last constant we will talk about, it is known as the frequency constant, and this is more related to when we actually take a disc of a piezoelectric element, let us say of a diameter dp and thickness t, and then we actually apply the voltage and we get it vibrated at its resonating frequency. Now, if I know this radial resonating frequency, okay, so the product of that with the diameter, that gives us one constant, and the thickness wise frequency product of that with thickness gives me another frequency constant. So, essentially these two frequency constant tells us that for a particular diameter or for a particular thickness, the higher the Nd or the higher the Nt, the higher will be the resonating frequency of the system. So, thus we are having 4 constants with us. Please keep in mind that d piezoelectric charge constant, and G that voltage constant, and then you have piezoelectric electromechanical coupling coefficient k, and finally this Nd Nt, that is the frequency constant of a system. So, with these 4 different types of constants, we should be able to define the behavior of a piezoelectric material. Say for example, I have PZT hard or PZT soft or PZT PVDF, you can see that how this D33 is changing. Okay. So, you can see that PMNPT shows us the largest value of this. Okay. You can also see that D31s are actually smaller than D33s. Okay. And you can also see that G3 from the sensing point of view, PVDFs are actually much better, okay, in comparison to both G33 and G31. In comparison to the piezoelectric material, PVDFs are much better. And you can also see that from the coupling constants point of view, PMNPT, which shows the largest piezoelectric effect, actually has the largest coupling coefficient. From the modulus of elasticity point of view also it is true, but however, this is more dense, so denser, and also it is something which is very brittle, it is not very easy to use. Okay. Free strain is once again very similar to the larger value of D33 or D31. So, you can see that free strain is maximum here, because it has the largest coupling coefficient, it has largest D33s etc. So, it has the largest free strain, and the smallest free strain is if you make a composite of positive PVDF, or otherwise PVDF is also having low free strain, but it is good in terms of voltage generation. What are the big points here? Composite of PZT PVDF, it has high electromechanical coupling with a moderate density, which is in between PZT and PVDF. Elastic modulus is quite high in comparison to PVDF. So, you gain if you make a composite, and if you make a composite, it will be a trade off between excellent actuation of PZT and excellent sensing of PVDF. So, it is a composite that is a desirable composite, you are taking the good parts of these two systems. Often we also put SMA in such systems and make PLZST, which is a SMA based piezoceramic composite, but that part we have not touched here. And this which is known as shape memory ceramic active material, it actually shows large strain. Okay. And however, such materials are still in the developmental stage. Now, we know the constitutive relationship. Can we have more symmetry based on the materials that we observe? In fact, we see that the common piezoelectric materials shows 4 mm or 6 mm symmetry. So, the outcome of this symmetry is that our elastic constants have this symmetry, and also piezoelectric charge constant, and also our strain tensor. So, if I use this symmetry condition, then actually our relationship becomes much simpler. This is the generic relationship. So, if you look at this relationship very carefully, that you have the first 3 terms sigma x, sigma y, sigma z, which are normal stress, right. So, these are your normal stress, and this is what is your shear stress. So, this is your shear stress, and D1, D2, D3, they are electric field displacement. In fact, if you if you integrate each one of them, you will be getting charge that will be stored in that area. Now, so you have how many? You have total 9 6 stress components and 3 electric field displacement components, and here you have this as the naturally the normal strain. So, these are the normal strain, and then you have the shear strain, this is the shear strain, and then you have this part which is electric field intensity, electric field intensity. So, you have basically supposed to have a 9 by 9 matrix, but in that matrix, because of the symmetry conditions and other material conditions that you observe, a good part of it is actually zeros, full of zeros. So, that will not give us coupling. In fact, if you look at it, that all normal stresses are coupled with the piezoelectric effect only through E31, E32, and E32 is E31 itself. So, only through that constants. So, that is how electric field intensity are coupled with the normal stress. Okay. In fact, that the normal stresses are not coupled, they will not generate in this particular piezoelectric material the shear strains. So, shear strains are generated by the shear stresses, right, that is diagonal part, and also some part of the electric field takes part in terms of generating the shear strain. But these shear strains are mostly sigma yz and sigma xz. You can see that sigma xy shear strain in this kind of materials cannot be generated by the electric field, because there is all the other terms are 0 here, all terms are 0 except C66. So, that means this part is non-smart in this group of materials. Okay. Then from the electric field displacement also we see a similar situation, that the electric field displacements can be generated from, say for example, if we are mostly concerned with D3 in the perpendicular direction electric field generation. So, that can be done from the 3 normal strain components if I deform, but not from the shear strains, okay, not from the electric fields at the other 2 directions, except from the electric field at the 3 direction can generate D3. So, these are the things that we have to keep in mind when actually using them as actuator or as sensor. If I ignore all other stresses, that is the normal stress sigma z and the shear stresses sigma xz and sigma yz for a plane stress situation, then we have only 2 of the normal strain and 1 shear strain. So, this Sx Sy as the 2 normal strain and Sxy as the shear strain, and D3 we get, which is the electric field intensity, electric field displacement. So, this electric field displacement is actually in the perpendicular z direction. So, that means, if I consider a plate like system like this, and if I denote this as x axis, as y axis, x or 1, y or 2 as I told you, and any this axis z as 3, then in this case you can see that we are only considering the charge accumulations at the top or at the bottom. Remember, I am always assuming a very thin layer of electrodes, a very thin layer of electrodes at the top and bottom, where these charges are actually getting accumulated. Okay. So, this is the simpler relationship, and in the plane stress conditions, which is what we normally use for a piezoelectric patch kind of a situation. Now, if we consider the strain that is generated in the system, then the strain will be having 2 parts in it. One is the structural strain, which is happening because of the force that we are applying, and the active strain. And the active strain component, if you look at it from the last equation, what are the active strains? In the case of Sx, the active strain is minus D31 sigma x. In the case of Sy, it is minus D32 sigma y. Sxy, there is no active strain. So, that is what is minus D31 E3 minus D32 E3, and there is no active strain in the shear direction. So, that is this is the total strain that actually comes into the system. Now, let us do one small example. Let us consider a thin piezoelectric plate, which is of size 25 mm by 10 mm, and thickness is 1.5 mm as has been shown here, and this is 25 mm length and 10 mm is the width of it. Okay. Now, let us say that in this one, and the piezoelectric material has an elastic modulus of about 65 gigapascal, Poisson's ratio of about 0.3, D31, D33s are known to us. Okay. Remember, D31 we give it with a negative sign, meaning thereby that positive voltage will be generating compressive stress in the system. Now, find out the strains if the plate is subjected to a voltage of 300 volt across, okay, and a force of 20 Newton along the x axis. Okay. So, I am applying a voltage and of 300 volt, I expect that it will expand, and I am applying a force of 20 Newton, which will also expand, and let us try to see that what are the strains that will happen if both of them are working on the system. So, we have a structural strain to calculate, we have an active strain to calculate. So, this is the active strain expressions that I already told you. So, by applying the voltage constants etc., we can get the active strain, which will come out to be about 10 micron strain, and the other direction also it is same. So, it will be about 10 micron strain. Now, we are applying the force of 20 Newton. So, that will give us in the longitudinal direction about 0.02 micron strain, and because of the Poisson's effect in the in the x direction it is expanding, this is x direction 0.02 by 0.02 structural strain. Okay. The other direction it is actually contracting. Okay. So, it is that contraction. So, is happening in this direction. So, here it is minus 0.006 micron strain. Okay. So, this is because of the Poisson's effect. So, in one direction it is expanding and in the other direction it is actually contracting. So, now, but in both the directions we have the active strain, which was about 10 micron strain. So, in one direction it will be added up, it will be 10.02, and in the other direction it will get subtracted, it will become 9.99 micron strain. So, this example thus tells us that how to calculate the strain in the system. Now, we come to model of the system. Let us say we are talking about two different ways in which piezoelectric patch can be modeled. One is called uniform strain model. Note here that you have two piezoelectric patches, one at top, one at the bottom of a particular beam type of a structure, but during deformation the strain is not changing in top and bottom. So, this is also known as uniform strain. Okay. Extension, this is extension time and this is the bending time. Okay. Even though the stress, this strain reversal is taking place in the rest of the beam, but here the patches it is uniform. The other model is that particularly when it is not surface bonded, it is embedded inside. Okay. During extension this strain is same, but during bending there is a variation inside the piezoelectric material also. So, that is the Bernoulli Euler bending. So, we have a uniform strain bending and a Bernoulli Euler bending. These are the two models that we can actually think of. Now, if you consider the Bernoulli Euler one, then the total strain as you already know from your ideas of composites has two parts. One is the midplane strain and another is related to the curvature Z kappa, where k or kappa is the curvature of the beam. And the total stress at any point will be having the stress that is coming from the structural part and also the stress that is getting generated from the actuator, the free strain blocking A lambda. So, that is the total stress. So, we can actually get from this the final equations of equilibrium by using all these conditions. We can get it as the E A times S S and E B times kappa. So, that will give us the P S plus P lambda. So, that is the total from the force balance point of view. Similarly, from the moment balance point of view, E B times S S and E C times kappa will give us M S plus M lambda. So, keep in mind that P lambda and M lambda, these are the active force and the active moment, whereas P S and M S are the mechanical load and the moment, the also to say you can also talk about in terms of stress resultant due to mechanical deformation and also the moment due to the bending of the system. So, that is your P S and M S. E A, E B, E C, as you can see, you can very easily find it out from if you know what is the modulus of elasticity and if you know that how this deformation is happening into the system. So, thus you can get an equation of equilibrium in the system. One is by the from the force balance and another is from the moment balance, assuming of course, perfect bending in the system. So, this is what is the first state of equations using Euler-Bernoulli model. In the next lecture, we will look into much more details of the uniform strain model. We will also talk about piezo actuators and sensors and various displacement and force measurement techniques. Thank you.